I will show the code in this video. This script config.py is a Python configuration file designed for this project. The script uses Yax package to create a structured hierarchical configuration with default values. The configuration is organized in several sections, each pertaining to different aspects of the project workflow, such as data handling, model parameters, training, and evaluation settings. In the data section, paths for the CityFlow dataset, JSON files for training and evaluation tracks, and image crop size are specified along with threshold value for identifying positive cases. The model section includes paths for BERT and model section includes paths for BERT and ResNet checkpoints and defines the output size of the model. The train section contains various training parameters like starting epoch, number of epochs, batch size, number of workers, frequency of printing logs, and clipping values for loss, learning rate settings, including momentum, weak decay, base learning rate, and step size for learning rate adjustment. The eval section is for evaluation configuration, specifying the path for restoring from checkpoints, path for query JSON, batch size, number of workers, and field for continuation evaluation. The script concludes with a function getDefaultConfig that returns a clone of the default configuration settings, facilitating easy access and modification of these settings in other parts of the project. This util.py script provides utility functions for logging in a Python application with a focus of integration with the TQDM progress bar and enhanced logging capabilities. The script defines two primary components, the TQDM logger class and getLogger function. The TQDM logger class is a custom string input-output stream object designed to redirect TQDM progress bar messages to a logger. Instead of the standard output, it initializes with a logger named TQDM and overrides the write and flush methods. The write method processes the buffer string by stripping specific characters, while the flush method logs this processed buffer at the info level. The getLogger function sets up and returns a logger with a specified name. It allows customization of logging levels, log message format, and option to save logs to different files based on the log level in a specified directory. The function uses the colorlog package to add color to log messages, enhancing readability. This setup is particularly useful for applications requiring detailed logs for debugging and monitoring, as it offers a structured and hierarchical logging system with the added benefit of visual clarity provided by colored logs. The vehicle retrieval dataset script defines two classes, CityFlow natural language dataset and CityFlow natural language inference dataset, which are subclasses of PyTorch datasets. These classes are designed for handling vehicle retrieval data from the CityFlow natural language dataset, a multi-target, multi-camera tracking benchmark. The CityFlow natural language dataset class is used for training and prepares data by loading JSON files containing vehicle tracks, selecting random natural language description, and corresponding image crops based on bounding box information. It also labels data based on predefined threshold and handles missing images by creating random crops. This CityFlow natural language inference dataset class intended for evaluation process tracks and constructs a tensor of cropped image for each track. Both classes are Both classes use the OpenCV library for image processing and PyTorch for data representation, ensuring compatibility with deep learning workflows. This script also integrates a logging mechanism with a getlogger function from the util spy script, facilitating debugging and tracking of dataset processing. The CMS baseline model script defines the CMS baseline model class, which is PyTorch neural network model for CMS architecture, particularly designed for a vehicle retrieval task using both visual and language data. This model integrates a modified ResNet-50 for visual embeddings and BERT for language embeddings. Here is the ResNet-50 model. The ResNet-50 model pre-trained on a custom dataset processes visual data, while BERT, with its tokenizer and model, handles natural language inputs. This script includes methods for forward computation to determine the similarity between language and visual embeddings. Loss computation for training using binary cross entropy and additional methods for calculating language embeddings and similarity scores separately. This approach is intended to learn a joint embedding space where similar language descriptions and visual data are brought closer, facilitating tasks such as cross-model retrieval or matching in the context of vehicle tracking and identification. The workflow PyScript is a comprehensive pipeline for training and evaluating a CMS neural network model, specifically designed for vehicle retrieval tasks using the Stiflow natural language dataset. It integrates distributing computing using PyTorch distributed data parallel for parallel model training across multiple GPUs and machines to configure various aspects of the training and evaluation processes, such as the number of machines, GPUs, and configuration file paths. The script also includes the setup for distributed training, dataset loading, model initialization, optimizer, and scheduler setup, and implements training loops with logic and checkpoint saving. For evaluation, it loads pre-trained model, process queries, and saves the result. The script is designed to be flexible and robust, allowing for efficient training and evaluation of the model on large-scale datasets in a distributed environment. When we run this file, we will wait like 1 minute. The epoch operations start, and where is my models? And these models will be created when this epoch is finished. Let's close this. It is workflow. The prepare output JSON PyScript is designed to organize the results of a vehicle retrieval task into a JSON format. The script specifies directories for the output files and desired JSON output path. It iterates each file in the output directory, reading its contents, and stores these results in a dictionary using the query identifier as the key. Each line in the output files is assumed to be an individual result related to the query and is appended to a list associated with the corresponding query key. Finally, the script writes this dictionary to a JSON file at the specified output path, organizing the results in a structured and easily accessible format. This process simplifies the aggregation of results from potentially numerous and disparate output files, ensuring a consolidated and standardized format for further analysis or reporting. Here's the results JSON. When we delete this file and run this code, results JSON file is printed. The OLED-Pi script is designed to assess the performance of a vehicle retrieval system by comparing its results against a set of ground truth data. It calculates key relation metrics, recall 5, recall 10, and MRR. The script first loads the ground truth data and the system's result. And the system's results from specified JSON files. It then iterates through each query in the ground truth, checking if the correct result is presented in the system's results and calculating its rank. If the target is within the top 10 results, the script increments and respective recall counters. The script also calculates the MRR, a measure of the average inverse rank of the correct results. These metrics, recall 5, recall 10, and MRR, are then averaged over all queries and printed, providing an overview of the system's retrieval accuracy and ranking effectiveness. This evaluation methodology is crucial for understanding the performance of retrieval systems in tasks like vehicle tracking in multi-camera networks. When we run this code, you can see that recall 5, recall 10, and MRR metrics. The extract video frames PyScript script is a Python utility for extracting individual frames from video files and saving them as images. It uses OpenCV for video processing and takes a directory as an input argument, which contains video files in its subdirectories. The script iterates over each subdirectory within the specified root directory, creates an image1 folder like that in each sequence directory. With each sequence directory, if it doesn't exist, and then process the corresponding video file. For each video, it captures frames one by one, saves them as JPEG images like this. This is my example video. It needs .avi format, and it will make my video frame by frame. Finally, we uploaded the project to Google Colab, but unfortunately we couldn't run it